students. In today's lecture, we are going to see the internal method of analysis of finding the kinetic parameters. As all we know that the rate equation will be having two kinetic parameters. One is called rate constant, other is called as the reaction order. So those data we have to, those informations we have to find by means of two methods. One is called integral method, other is called differential method of analysis of kinetic data. See, now in this lecture we are going to talk about the integral method of analysis of like kinetic data. Actually this method is the trial based method. Normally what we do is that in this method we assume the reaction order. Let me to say the general rate equation is minus RA is equal to minus dCA by dt is equal to K into Ca power n. Now our interest is to find the value of K and n. Now according to the method we have to assume the reaction order. Let me to say I assume the order as n is equal to 1. Then the rate equation becomes like minus dCA by dt is equal to K into Ca. So that equation now becomes like a differential equation. The variables are rearranged, like Ca is taken to the other side, the time is taken to the right hand side. So after doing that the equation is integrated between the limits. So here the variables are concentration versus time, the data we are having from experiment. So the equation is now integrated. After substitution of the limit in the equation, we get one final form. That equation is called as the rate equation in integral form. So this method is a trial based method where we have to guess or we have to assume the reaction order. Like n is equal to 1 we have to assume, then frame the equation, then try to fit the data from experiment in that equation, and you have to see the trend of the graph. Actually we have to plot a graph between time versus concentration. That graph, if it is fitting the equation, then our assumed order is correct. If it is not so, then we have to assume some other order, then the procedure should be repeated once again. See, now I am going to explain this method with a simple example. Say for example we have a reaction of this type, like we have a unimolecular first order reaction we are having. So it is a liquid phase reaction, A is giving us product. Now I am assuming that the reaction is obeying the first order kinetics. So for a first order reaction the rate equation is given like this. So minus R is equal to Kca power 1. So this equation is now rearranged, like take that Ca concentration term to left hand side, time variable to right hand side, and then between the limits when t is equal to 0, starting point the concentration is Ca0, at any time t the concentration is Ca. As all we know that dCA by Ca will give you ln A. For that result, when the limit is applied, I get the equation like this, in this form, minus ln Ca by Ca0 is equal to Kt. So now this equation looks like y is equal to mx form. For example, if I take this concentration term as y variable, this t as x variable, so this equation looks like y is equal to mx form. Okay, see now what we are supposed to do is, already we have the data between time and concentration from experiment. So that data should be fitted in this equation. Suppose if I get a straight line passing through origin, because this equation looks like y equal to mx form. It is obviously a straight line passing through origin form. So when I fit the data from experiment in this equation, if I get a straight line passing through origin, our assumed order is correct. If it is not so, then I have to assume some other order for the reaction. Now this is the concentration time form. This equation can be converted into like conversion versus time form also. For that we use a relation between the fractional conversion. So here the Xa is called as the fractional conversion term. This is nothing but the moles of A reactor divided by initial number of moles taken. So this is the integral equation, the equation number 11, equation number 12. So they are the integrated rate expression for a first order reaction. So now this is the graphical form. You can see that minus ln, this equation we saw already in the previous slide, minus ln Ca by C0 versus t. As you can see that when the data from experiment is plotted in the graph with the help of this values and all, if I get a straight line, then the order is order is equal to 1. If it is not so, suppose if I get some curve, the type of trend means, then I have to go for some other order for the reaction. So this method is a trial based approach where we have to assume the reaction order. That is for the first order reaction. That case is now considered. You can take for one more example also. We have a special type of reaction called as a zero order reaction. We know pretty well what is the definition for zero order reaction. This means that the rate does not depend on the concentration. As you can see here that this equation is not having any concentration term. Ca power 0. That means the rate is not depending on the concentration. Even for this reaction also, like this type of reaction also, we can apply the integral method to find the value of, our aim is to find the value of K, because we assume the order already. Order is known to us, we assume the order, so we need to find the K based on the data from experiment and based on the final equation whatever we got here. For example, for zero reaction, after integration and then applying the limit, the final equation is coming like this. So this equation, when it is plotted, as you can see that the Ca versus T graph is plotted, we get a negative trend here, negative slope. Or if we plot the graph between Xa versus T, we get a positive slope. The slope value is K by Ca naught. So from the slope from the graph, that is equal to K by Ca naught. Since Ca naught is known, we can able to find the value of K. So by this method, we could able to comfortably find the value of the kinetic parameters. So in this lecture, we have learnt how to find the complete rate equation for a chemical reaction. So thanks for listening.